Hey everybody, it's Mr. N here. Let's take a look at this review. This is a little extra practice on derivative graphs, interpreting the information that we can obtain when we view the graph of a derivative. So this first one says, given the graph of f prime of x, state the intervals where f of x is increasing and decreasing. So basically, we are told that this graph right here is our f prime graph. So let's go ahead and label that, and we will call this f prime. And we want to know the intervals of increasing, decreasing. Now the method I taught you guys that I really think is beneficial is the number line method. So what we're going to do is we're going to create a number line right here. And on this number line, this is going to be f prime. And so I'm going to look at my f prime graph, and I'm going to determine where it is the zeros, where it is above the axis, and where it is below the axis. Because for increasing and decreasing, we want to know when f prime of x is greater than 0 for increasing and when f prime of x is less than 0. In other words, we want to know when the slopes of the tangents are positive and when the slopes of the tangents are negative. So this basically is the graph of the slopes of the tangents, f prime. So let's find out when it's 0. It's 0 at this point right here, and we're going to take a look at that, and we're going to say that's about negative 2.75. It's 0 right here at negative 1, and it's 0 again at 4. And so let's go ahead and look at the intervals here. In this section right here, it's above the axes. So I'm going to label this as positive right here. In this section right here between negative 3 to negative 1, it's below the axes. So I'm sorry, from negative 2.75 to negative 1, it's below the axis. So I'll go ahead and label these as negative. And then from 1 right here to 4, it's above the axes again, and then below the axes. So these are my intervals of increasing, decreasing. So we'll write this down, and we'll say it's increasing when f of x is greater than 0. So that's going to be from negative infinity to negative 2.75, and from negative 1 to 4. And so that means it's decreasing from negative 2.75 to negative 1 and 4 to infinity. Okay, moving on to part B. It says state the x-coordinates of any local extrema of f of x and indicate if these are relative maximums or minimums. Remember, the possibles that we're looking for the extrema are our critical points, and this is when f prime of x equals 0 or is undefined. That's what we're looking for. Well, there's no undefined points in this, but we know that there are parts there it is 0. So it does cross through 0 at negative 2.75, and it crosses right there at negative 1, and then again it crosses at 4 right over here. So we're just going to estimate that to be 4, as we did before. Okay, so let's go ahead and take a look and determine these are possibles. How do we know if they are for sure? Well, we have to examine these on our number line. We see that the slopes at negative 2.75 increase before that, and then they decrease after that. So this ends up being a relative maximum. Over here we have negative slopes to a positive slope. That ends up being a relative minimum. And over here we end up with positive slopes to negative, so that's going to be a relative maximum. So let's go ahead and write that down because we examined it from our number line, and we'll write these solutions down. So what we have here is we have relative maximums at x equals negative 2.75 and x equals 4. We have a relative minimum at x equals negative 1. All right, now for part C, it says state the intervals of concavity. So for concavity, we want to do a similar process, but this time we're going to put a number line, and on our number line we want f double prime. So let's find out when f double prime, the second derivative, is 0. Well, we're going to take a look at our derivative graph, and we want horizontal tangents. Wherever we end up with horizontal tangents on our derivative graph, that's when the second derivative is going to be 0. And that occurs over here at -2, and then it occurs again here at +2. So we've got two spots where we end up with a horizontal tangent. So these, let's state our intervals. So actually, let's find out what happens in between. So from negative infinity to -2, when I look right here, these are all negative slopes. So on my number line, I'm going to list these as negative slopes. From -2 to 2, from in this region right in here, these are all positive slopes. So we'll go ahead and list these as positive slopes. And then from 2 to infinity, we end up with negative slopes again. So we can say that this is concave up from -2 to 2, and concave down from negative infinity to -2, and from 2 to infinity. So for points of inflection, we're going to use our similar second derivative graph and see where it changes concavity, because points of inflection, we want to know when f double prime of x equals 0 or undefined. This gives us our possibles, and we've already listed those, -2 and 2. So sometimes it's easier to do the number line always first and then find all the information. So from this, we could see that it changes from negative here to positive, so that's definitely an inflection point, and from positive to negative over there. So we have two inflection points, and it changes concavity at x equals -2 and at 2. So now for our final part here, we want to sketch a graph of all of this put together, all this information. So let's see what we can do. We have a maximum that occurs at -2.75. So -2.75, we've got a maximum. I'm just going to put a point way up there. Again, this is arbitrary. You could have put it down here, right here. You could have put it down lower. It doesn't matter. Again, we are only looking for x coordinates here, so technically I can just get rid of the y part because I just need to know when it reaches a maximum, when it reaches a minimum. I don't have enough information right now to go through and find those exact ones, although I can try to interpret it from the graph, but we don't have an initial condition, so we can't completely do this. So in any case, I have another maximum that occurs at 4. So let's put a maximum at 4, and we're going to put that, say, like right there, just a little bit lower. Now, since these are maximums, we end up with a curvature that looks like that and like that. This is possible. There are other situations, but this is possible. And then we have inflection points at -2 and 2. Oh, let's go ahead and put our relative minimum. And the relative minimum occurs at x equals -1. So we have a relative minimum here somewhere at -1. And at -2, we have a point of inflection. So our relative minimum like this. And this is a point of inflection. So that's where it changes concavity right there. And then we have a point of inflection at 2 somewhere. We can put it like right here, say. So this graph maybe comes up like this, and this is the point where it changes concavity. So this part's concave up, this part starts going concave down, and this is all concave down here. And if you look at the intervals of increasing, decreasing, yes, it's increasing along this, it's decreasing all along here, and it's increasing here, and then decreasing. So this graph is a possible sketch of what's happening. All right, let's move on to number 2. So let's go ahead and slide this up and take a look at what number 2 is asking. Number 2 says, use the graph of f shown to estimate the values of c that satisfy the conclusion of the mean value theorem from -2 to 4. So at -2, we have a point right here, and at 4, we've got a point, and we'll put that right there. And we need to use the graph of this is our f of x graph, to find any values of c that satisfy the conclusion of the mean value theorem. Well, MVT basically, in a nutshell, states that the secant and the secant connecting the two ends here from this end to that end will have spots where the tangent will be parallel, so they'll have the same slope. So what we need to do is we need to draw the secant. So let's go ahead, and I'm trying to find a straight edge here, and I will connect these 2 points as best as I can. This is going to be kind of tough with this, so let's see how well I can do this. I don't have a straight edge here, but I do. Let's see if we have a little drawing tool, and let's try to do this. There we go, we connected it. So now we need to find spots that are parallel to this. So let's use that drawing tool again. And right here is a spot that is parallel to it. And right here is a spot that is parallel to it. That didn't work out so good, so let's see if I could redo this a little bit better. Right there. And then we need another one that's parallel, and we can see that there's one right here, and I'm gonna just freehand this one. So this one is parallel to it right about right there. So I tried to draw those as best as I could parallel, because again, we're just estimating right now. And let's read these off. So this is at about 0.75, I would say, because this is the value of 1. So we're going to estimate C over here to be about negative 0.75. And then we've got a spot right here. I'll estimate this to be about, that's about 1. So C is 1. And then I'll read my graph off over here, and I'll estimate this point to be about, well, there is 3, and that's going to be 2.5, so we'll say about 2.6, so approximately 2.6. So again, the key to this question is just to realize you have to draw this secant right in here. Let's use a different color to highlight it for you. You got to draw this secant right in there, and then you're going to find tangents parallel to that, and then you can just use a straight edge to do that, to estimate it, and then find what the x values would be, and that's your value of C. All right, let's take a look at our next page here and see what we got. Let's go ahead and enlarge this. Hopefully you guys can see that I enlarged that so that we can look at it a little bit better. It says, in the figure below, the graph of f prime, the derivative of the function f on a closed interval from -4 to 4. The graph of f prime has horizontal tangents. Okay, they're clarifying here that these are horizontal tangents that we see. So let's go ahead and indicate that. These are at x equals -2, x equals 0, x equals 1/2, x equals 2. So those are horizontal tangents there. So those are the points it goes through. And then the function f is twice differentiable. In other words, I can take the second derivative of it. So there's continuity involved, with f of -1 equaling 3. Oh, so now I'm given an initial condition. This is my initial condition. So this might help me later on graphing it. So for part A, it says, find the x-coordinate of each local maximum or local minimum or maximum on the graph of f and justify your answer. So what I want to do here first is I want to always go back to that number line method. And I'm going to make my number line, and we'll go ahead and put it right here. And on my number line, this is f prime. I want to find certain critical points and put those on my number line. The first one that I see occurs over here where it's a 0, then that's going to be at -3. So that's a 0. This is where f prime of x, this is our f prime, this is where f prime of x equals 0 or undefined. Since I know it's twice differentiable, we're not going to have any of those undefined points on this one right now. Okay, so then I have another point where it crosses right here. This is at 0. And then I have another one here at 1. And then I've got another one over here at 1, 2, 3. So these are my zeros on f prime. So now let's see where it's above and below the axis. From -3 on this side, all of this is above the axis, all of this is below the axis, so above here, these are positives. In this range, it'll be negatives. So let's go ahead and write that in. So in this range, we've got positives. In this range, I've got negatives. And look what happens though. I hit 0 over here. These are all below the axis, and it still stays, even though I hit 0, it still stays below the axis all the way to 1. So these will also, again, be negatives, then positives, and then from 3 to infinity, we end up with negative again. Actually, they tell me it's from 4, so I'm only going to 4. So from 3 to 4, we end up with the negatives. So let's go ahead and find any relative maximums or minimums. So look at this right here. Positive slope to negative slope. Negative slope to positive slope. Positive slope to negative slope. So my local maximums, so this is a maximum, and this is a maximum, and this is a minimum. So my local maximum occurs, remember local and relative mean the same, at x equals -3 and x equals 3. I have a local minimum at x equals 1. And we've tested these. We've already indicated that our critical points, we indicated above, were at x equals -3, 0, 1, and 3, which were on these line graphs. So the line graph basically gave me all the information I needed. Okay, so for part B, it says find the x-coordinates of each of the points of inflection of the graph of f and justify your answer. So for the points of inflection, we need concavity. Look at part C. It says find the intervals on which f is concave up and also has a negative slope. So let's go ahead and find our concavity. And then we can determine our points of inflection. So to do that, we need to go ahead again, and I'm going to do f double prime this time, the number line for that. And we're looking at our graph, we're looking at the horizontal tangents, and up above it also told me those are horizontal tangents. So let's go ahead and put these on a number line. And this occurs at -2. I have a horizontal tangent. I have one at 0. I've got another horizontal tangent right here at 2. And notice I'm trying to line it up. I'm not sure if you could tell, but let me show you here. I'm trying to line it up so that it's on the same, roughly same scale as the f prime, because I'm going to be comparing things in part C. So I went ahead and read the problem so that I know that I'm going to be comparing things, so I lined it up. All right, let's see what's going on here. Oh, we also have one more. I forgot about this. 1/2 right there. All right, so let's look at the slopes. The slopes here are all negative, then they turn to be positive, then negative, then positive, then negative. So it just keeps flip-flopping. So in each of these intervals, we just flip-flop. So this one is going to be negative, we said, positive, negative, positive, and negative. All right, since we are looking for the points of inflection, this is where it changes concavity. So we need changes concavity. So what we needed to do is we needed f double prime of x to be 0 or undefined. We didn't have any undefined on this one, but we did have 0, so our possibles were at x equals -2, 0, 1/2, and +2. We tested them on the number line, test on number line, and we ended up perfectly with every single one of them working. It changed concavity at each one of these spots. You could see negative, positive, positive, negative, negative, positive. So each one of these ends up being an inflection point. So inflection points at x equals -2, 0, 1/2, and 2. All of them. All right, for part C, it said find all the intervals on which the graph of f is concave up and has a negative slope. So concave up and a negative slope. So this is what I wanted to do when I compared these. I'm looking at these regions. So if I draw this like this and I draw that like that, here's the 0, here's the 1/2, here's the 1, and here's 2, and here's 3. So I'm looking for concavity. I want concave up, and I want a negative slope. That means f prime has to be negative. So, because f prime was below the axis, so that gave me a negative slope. Now I'm looking for these intervals, and you could see, start with the concavity ones. We know that this is negative all in here. Concave up right here, negative slope. Oh, that happens from -2 to 0. So this happens from -2 to 0. Let's see, does it occur anywhere else? Well, I'm looking at this. I need positive concave up from 1/2 to 2. It's concave up. And oh, look, right in here. This is a negative. This ends up positive. So from 1/2 to 1, it continues on like that. And then so we see that this, again, like I said, occurs from 1/2 to 1, where this is concave up. These are positives, but yet it's negative with the slope. So this is union 1/2 to 1. All right, let's go ahead and move on to the final question. It says, sketch a possible graph of this. All right, well, let's start with the maximums. We know, well, let's first start with the point we're given. We're given that it goes through f of -1 equals 3. We know that there's a maximum that occurs at x equals -3 and x equals 3. We know that there's a relative minimum that occurs at, let's go back up and look, that was at x equals 1. And we know we've got some concavity and we know some inflection points. So let's kind of see what's going on here. We know, first of all, that it goes through the point -1, 1, 2, 3. So we're going to put a point right there for sure. Then we know that at -3, it reaches a maximum. 1, 2, 3. We'll just put a maximum up here. We know at 3, it reaches a maximum. 1, 2, 3. Again, this is arbitrary where I put these points. 1, 2, 3. I could put it way up here. I could put it down here. Let's just go ahead and put it right here. Looks good for now. And at x equals 1. I can calculate these exactly. If I knew the exact slopes at those, I could find those actual points, but we're going to bypass that right now because it just says sketch, and it's a possible graph. So we said at 1, we're going to have a minimum, so let's go ahead and put some minimum value, and I'll just put it way down here. You could have put it here. Again, you could. It doesn't matter. You can put it in any spot, but I just chose to do it right there. Now we have, so it has to come through these points. Somehow it has to go through this value right here. And before I completely connect it like that, I want you to understand that this can change concavity in here. And in fact, it does. Look at -2. It changes from concave. If I can move this right down right here, you could see at -2, it changes from concave down, and I'm looking right here, to concave up. So let's go ahead and put that in there. It goes concave down to concave up. So drawing this, we're going to end up with concave down and -2 concave up. So this part is concave down. This part is concave up. And it continues its concave up until it reaches 0. So it's concave up until it reaches 0. So it goes through this point, concave up until it reaches 0. So it flattens out because we know there's an inflection point right here. Or we know it goes through this point. Okay, so what I'm going to do is I'm going to just kind of redraw this a little bit here. Just so you can kind of see what's going on. So we know that this is an inflection point, and at 0 we said that it begins to be concave down again. And then we know at 1/2 it hits another inflection point, so it ends up being concave up somewhere over here. So this is up, this is down, all of this is concave. And I gotta somehow extenuate that so that it shows that it's concave down. So I'm gonna do that like that. And then it continues concave up. Then it hits another inflection point at 2, where it turns and changes its concavity. So this is a possible graph of our situation. And we're only going to go to 4 because it said from -4 to 4. So same thing on the other side. We're just going to go to 4. So again, this was all our concave down, and you can check on intervals increasing and decreasing, and you'll see that we're increasing, decreasing, goes through this point, hits an inflection point right there, so it turns, it changes its concavity. This is the up shape, and then the down shape again. All right, kind of a rough sketch, but that's all they asked for. So hopefully this has helped. Good luck studying, and good luck with interpreting your derivatives.